Alright, so the next big thing, one of the biggest things in our firmware is the ADC10 interrupt service routine, and this is a little bit complicated and a little bit confusing. So I guess to start off, we need a little overview. The room temperature sensor is the microchip MCP9708, and it outputs an analog voltage of 10 millivolts per degree C. But if you read the data sheet, the way this chip works is it at 0 degrees C it puts out 500 millivolts because it can go from negative something C to positive something C, and so the voltage at negative whatever its lowest temperature is 0 volts, and then it goes up from there. So by the time you get to 0 C, you're at half a volt. So we have an offset of 500 millivolts we have to subtract off of our room temperature. So that's what this 250 is, and we'll go through all this, but just keep this in mind. The 250 is 250 samples, and each sample is 2 millivolts, so that's our 500 millivolts. So I guess to mention all the stats, we have a 2 millivolt sample per sample resolution, and that's because, remember, we use an external voltage reference of 2 volts for our ADC10, and it's a 10-bit analog to digital converter. So if we take 2 volts and divide that by 10 bits, which is 1023, we get 0.001955 volts. And if we multiply that by 1,000 to get it in millivolts, we get 1.9 millivolts. So we get roughly 2 millivolts. So I'm just going to call that 2 millivolts. So that's how we get our 2 millivolts per sample for the analog to digital converter. And so when we sample the MCP9708 to get room temperature, we're at 0 degrees C, we're going to get 250 samples, because in the data sheet, microchip says that at 0 degrees C it's going to output 500 volts. So since everything's going to start from room temperature, and 0 degrees C is kind of where we're starting, we're going to subtract off a half a volt to get us up to 0 degrees C, so that all of our temperature stuff is based on 0 degrees C and up. It's kind of a way to normalize our temperatures. So that's, when we get down here, keep that in mind because it's a little confusing. And so the first thing that we do is remember how this works. It samples all 12 channels, and then the DTC stores all 12 samples in a 12-byte array, and then it throws an interrupt. And that interrupt is this interrupt. And so when it throws the analog to digital converter interrupt flag, we're going to execute this. So what happens most of the time is we get an interrupt saying the DTC is done, we've got our 12 samples stored away, and we're done. And so we're going to come in here, and we have a counter that counts up to 128. So what happens is we take 128 samples of the thermocouple and the microchip temperature sensor, and we store those in this long integer. I think it's a long int. And so effectively what we do is we are taking an average. We sum up 128 samples of the temperature sensor and the A to D. This is just the temperature. This is a temperature sensor too, but we're summing up in half degrees C instead of 1 degree C like up here. So we get to this line, we add up 128 times our thermocouple sample temperature. We shift this to the right 4 because, remember, our thermocouple temperature, after going through all the analog stuff that I've got to condition the signal, we end up outputting 8 millivolts per 1 degree C. So what we need to do is we need to get that down to one sample is 1 degree C, or this number represents one digit is 1 degree C. So to do that, if we output 8 millivolts per degree C, then our samples will be 4 samples per degree C, because each sample is 2 millivolts. So every time we sample the thermocouple, we're going to get 4 samples per degree Celsius. So we want to divide that by 4, so that'll give us 1 sample or 1 digit per degree Celsius. So that's what we do in the first line. The second line is where we get a half a degree Celsius, and that's used in our CCR0 time array 0 algorithm for a little higher resolution. And what we do here is we take those 4 samples and we divide them by 2. So we divide them in half. So remember that the thermocouple is an analog device. It outputs an infinite number of voltages between any 2 voltages. So all we have to do is we have a bigger number for ½ degrees C. So that's what we do there. We take our result, which would be 4 samples per degree C, and we divide it by 2 to get 2 samples per degree C. So that number is going to be 1/2 degrees C. The last thing that we do is we sum up all of our room temperature samples. And so here we haven't messed with the offset or anything. We're literally just taking the value at 2 millivolts per sample, and we're storing that number of samples from the microchip temperature sensor into this room temp sum. And so we sum all 3 of these up 128 times. Now down here we'll start with room temp average. So our average room temperature is going to be our room temperature sum divided by, well, yeah, our room temperature average is going to be our room temperature sum divided by 128. So this right shift 7 is the same thing as dividing by 128. We shift to the right 7 times, which effectively divides this number by 128. And the reason I picked 2 millivolts per degree C is so I can evenly shift and divide by 2, and I have most of my data in factors of 2. And really that was for the thermocouple. This didn't work out quite so nice. I really needed to divide by 10, but we'll get to that in a minute. So I divide by 128 by shifting to the right 7 times, and then here we subtract off the offset. So remember, we talked about that. Subtract off a ½ volt, which is 250 samples. So this doesn't give us our room temperature in degrees C, though. This room temp average is not quite in 1 degree C per 1 digit yet, because remember the microchip chip puts out 10 millivolts per degree C, and so when we sample that, we get 5 samples per degree C. So we sample all that, sum it up 128 times, divide by 128 to get an average number of 5 samples per degree C. So that's some big number. And then we subtract off the offset to give us our temperature from 0 degrees. But the problem here is we still need to divide by 5. And so what I ended up doing is figuring out how to divide by 10. You can divide by anything, the method I finally got working, but initially I picked 10, so I wanted to stick with that. So since it's 5 samples per degree C, I needed to double that so I could then divide it by 10 to get 1 sample per degree C. So here all I do is add it to itself, which is the same thing as multiplying by 2. So now I've got 10 samples per 1 degree C. And so now I need to divide room temp average by 10. And we'll get to that a little later, so just keep that in mind. We're now, our room temperature through all this, which is kind of confusing, I understand that, but we're at 10 samples per degree C. So now we just need to divide by 10 and we can get our 1 sample or 1 digit per 1 degree C, just like you'll see we've done below with the thermocouple temperature. Now the reason I picked a 2 volt reference to give me a 2 millivolt per sample is because the thermocouple puts out 8 millivolts per degree C, and that's all going to be explained when we go through the analog section. But so we've got 8 millivolts per degree C, and our A to D has got 2 millivolts per sample, so that means that for every degree C we're going to have 4 A to D samples. So it's easy to digitally divide by 2, 4, 8, 16, 32, 64. All we do is shift. So we summed up 128 values. Now we need to divide by 128. Well, actually, the divide by 4 is up here. I already went over that. I forgot. But so since we're already in 1 degree C per 1 digit, because we divide by 4 here, because our millivolts per sample worked out in powers of 2. Now all we have to do is divide by 128 to get our average. So for this, all we're really doing is dividing so that we can get a good average temperature. And you usually do this in digital systems. This is pretty common. So here we right shift 7 times to divide this by 128 because we've summed up 128 of the values. And here we right shift the half temperature we right shift that 7 times to divide that by 128 because we have 128 of those samples. So hopefully this wasn't impossible to follow, but basically what we're doing is averaging up with all this. We are averaging up our temperatures. We're just taking a 128 point average so that we have more reliable temperature information to send to our GUI. Now this was used because I kind of solved the same problem in 2 ways, and we'll talk more about this with the GUI, but I had to send all this data across to the GUI. So I initially, instead of dividing by 10 on the MSP, because I wasn't sure how to do that, I initially just broke this room temperature in half and sent it off to the GUI and divided by 10 in Python because that's a lot easier. Turns out I figured out how to divide by 10 pretty efficiently. Well, maybe not pretty efficiently, but it's worked out pretty well. So you don't have to do it this way. This is one solution of 2 solutions to getting the data over to the GUI. Well, really to getting a value on the GUI that's 1 degree C per 1 digit for the room temperature. Because what you want to do is you want to take the room temperature and the thermocouple temperature and add them together to get your real temperature. So that's why I need the room temperature. So what I ended up doing was breaking this in half because this room temp is a big number. Remember, it's not one digit per degree C. It's 10 digits per degree C. Remember, right here, right here, we multiply by 2 because we have 5 digits per degree C. Multiply that 2, and that's only because I picked 10, and I was going to try to divide by 10. You could just do all this, forget this, and then divide by 5. But I ended up going through all this with 10, so I wanted to stick with it. So I broke it in half, and you'll see in the com links we send room temp 1 and room temp 2, and that's where they come from, because when I did the comms, it was easier for me to break this in half, send it to Python, have Python divide by 10, because it's as simple as saying, you know, room temp 1 divided by 10, and you get an answer. In the MSP, it's not that easy. So that's that. Then down here, we just reset everything, reset our flags and counters. Down here, we reset our address for our array, so that when we run through the sequence of channels again, we'll start back over at our array 0, our ADC 0 array address. We clear our flag, and then we restart our sampling sequence. And remember, this only interrupts after all the samples are taken and stored by the DTC. So we restart this whole sequence again. And so we do this constantly, and we do this 128 times. After 128, we take all these averages and save them. So everything in here is what we're working off of with the temperature algorithms and control algorithms. Okay, next we'll go on to the main controller and the division routine. I hope this made at least a little bit of sense, and I guess this is definitely by far the most confusing part, this room temperature stuff and the division stuff, but it'll all start to come together in the end.